Hello, welcome to this channel. Today we will go to design hemispherical dielectric resonator antennas. So before going to this design, if you want to design rectangular and cylindrical dielectric resonator antenna, then check my previous videos, that is design 1 and design 2, and you will get the complete design as well as empirical formula for the corresponding antennas. So now we'll start the design. So before going to this design, you should know then how to design the hemispherical dielectric resonator antenna, what are the parameters, and how to choose the dielectric constant for the hemispherical dielectric resonator, and what are the empirical formulas in order to get the dimension of hemispherical dielectric resonator antennas. So this one is the empirical equations. So Fr is the resonant frequency and this is the parameters. So by putting the all parameters, you will get the Fr resonant frequency for the hemispherical dielectric resonator antennas. So this ER is the epsilon R for dielectric resonator antennas, and these are the different parameters. A is the radius. So accordingly you will calculate and you will get the resonant frequency for the particular applications. Now we will start the design. So this is the workspace for designing the antenna. So this is 3-layer structure. First of all we will design the substrate, then below the substrate we will design the ground plane, and above the substrate there will be the resonators, that is hemispherical resonator. So we need to click this one, and here you need to select, and this is the substrate, and here I have taken this one is minus 25 plus 25 minus 25 plus 25. This one is 0, and so the thickness of the substrate is 1.6, and here you need to select the material. That material is Fr4. So always you have to select the lossy materials. Here being dielectric constant is 4.3 and mu is 1 and tan dial is 0.025, and this is load. So this is our substrate, and below the substrate we need to design the ground plane. So here you have to select this face. Directly we can design. This is the face is selected. Then there is the options. We can directly design the ground plane. So extrude option. So this is our ground plane, and thickness is 0.035, and our material is PEC. Now this is okay. Now it is designed. So if you want to change the color, then here you will go to the assign the materials, and here you can put the different color. Okay, so this is our main design. Then we'll design the dielectric resonators. Then here we will design the hemispherical. For that you need to select this sphere, and we will cut the half of the sphere, then we will get the hemisphere. This is dr, and so this radius is 7.5 as per the calculation, and this one will be 0 because we will place our hemispherical dr at center, and we need to load the materials. So here we will use the aluminum material having dielectric constant is 9.9. Load it and preview. Just you see the sphere, then we'll go for the hemisphere. Okay, this is cancel. Then we need to shift this dielectric resonator into top side. So for that you just click P. This is the point, and here also we need to select one point. So we got both the point. Then you select this dielectric resonator, then Control T, that will be transform, and it will be okay. Then what's happen, our dielectric resonator came to top of the substrate. So we'll change one material color, so it will be looking good. Yeah, then we'll cut this sphere. Then you select over here this peak bottom of the sphere. Then we'll use our local coordinate align over here. Then we'll design one box. So this one will be cut, and so here height is important. This one will be 7.5, and let's see, take the different one and we'll see. So this one will remove, so cut it, cancel. Then how to remove this bottom part, means how to convert our sphere into hemisphere. First of all you select this one, then Boolean, subtract, then select this cut and enter. Now we got this hemisphere. Then how to bring this hemisphere into bottom surface of the substrate. So at that time what you have to do, there is one simple shortcut you have to apply. Just press the A and automatically this one will come, and select the face, bottom face. Again press the A, then select over here. So that means this is the middle point, and this one also middle point, top of the middle point. Then again select the dielectric resonator, then Control T, then it will come to bottom, surface of the substrate. Now it came to surface of the substrate. Now we will design the feed line. Now we will design the feed. So for that just click the M, and this one will automatically come, and select over here and align this our local WCS, then it will come here. Then we'll go for designing the feed line. Okay, so this one is feed, and this one will be minus 3.7 divided by 2 plus 3.7 divided by 2. So this is not the perfect optimized width of the feed, so you can optimize and they will get the better return loss also. And this is V0 to 23, that a little bit I optimized it previously, that's why I took that value. and this thickness of the feed is 0.035, and of course this material will be the PEC or copper, and it is design. So here we will change the color, it will be look good, it's yellow. Okay, then we will apply the feed, then we will apply the excitation, input excitation over here. Okay, so for that we need to select the surface, face surface. So here you can directly select the, press the F, and you can directly select the surface also. This is the surface. Then there is one option, that is macro, that is means go to the home, and here VBA macros. If you are using 2024, then it will come VBA macros. If you are going means if you are using lower version, maybe only macros options are available. Then go to the solver and port, calculate the port extension coefficients. So it will automatically take that width of the feed and height of the substrate, and what is the dielectric constant, that automatically they calculate by the substrate. No need to feed the WH and epsilon r, and it will calculate the extension coefficient, that is 7.43, and K value should be lies in between 7.43 to 7.43, that is given. So construct the port from peak face, then close. So this is automatically, it will come to the port. Then go to the simulation, setup solver. So if you are not feeding the frequency from starting onwards, then if you go for run of this program, then automatically they will ask for the frequency. Then you have to feed the frequency as per the application. Then this is 4.7 to 7 gigahertz. Okay, then it will start the programs. So it will take 4 to 5 minutes. It mainly depends upon the performance of the systems. So it is running. So before simulating the programs, you should save the program. So I have not saved, but you need to save the programs. Okay, now the simulation is completed. We will check the results. For checking the S parameter, you go to the 1D result. Here S parameter is there, so you click this plus symbol, then you will get S11. So as per our calculations, it was 5.9 gigahertz. Now also we got the 5.9 gigahertz. So you check it, what is the peak resonant, 5.89, that will nearly about 5.9. So 5.9 we are getting minus 16 dB return loss. So like that you can improve this return loss by adjusting the width of the feed. Like that you can go for the optimizations. Then if you want to see the far field result like gain or like gain, then you need to select this field monitor, then right click new field monitor, then here there is an option far field, RCS. So if we'll go for broadband, then it will be give the result from minimum frequency to maximum frequency. So we have taken 4.8 or like that, from 4.8 to 7 gigahertz it will show. And if will means this one will take the more time. So in order to avoid the reduction of this time, you need to select this particular frequency whatever we need. Actually our record frequency is 5.9 gigahertz. Then you select apply and OK, and again you need to simulate this. Here it came far field 5.9. then after simulation it will show the far field. Let me simulate this one also, it will be good. Yeah, simulation is going on. Simulation is completed. Then we will click this far field. Here we got the far field at 5.9 gigahertz because we selected only 5.9 gigahertz, that's why it came. And click it, then it will show the gain in dBi, that is 7.06. so if you want to large this radiation patterns, then here there is an option to increase, and you can go for this structure transparent and far field. So various options are available, so as per the requirement you can go for the selection of the structures. So this is all about the hemispherical dielectric resonator antenna. Those who want to continue the research of hemispherical dielectric resonator antenna, so and if you want to generate some empirical formulas, for easy empirical formula you can refer this video. And if you want to design some modified hemispherical dielectric resonator antenna in order to improve the performance of antenna like gain or bandwidth, then you can use this simple structure of hemispherical. Then we'll go for design 2, that is modified structure of hemispherical dielectric resonator antenna. So accordingly we'll go for various kinds of new structure by considering the simple structures of hemispherical dielectric resonator antenna. So with this we end this video, and so if you like this video, then you share, subscribe, and thank you for watching. So next video I will upload some different kinds of dielectric resonator antennas, like modified dielectric resonator antenna, in order to improve the performance of antennas. So thanks for watching.